Welcome to a highlight of this course. I am proud to introduce the star of calculus. No, not you, Merlot. Get out of the picture. Let me continue. The derivative. Applause, 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 everybody. I introduce the derivative today. And I'm introducing two other concepts which are very, very close related. The one is the slope of the tangent line, which means, of course, I will introduce what the tangent line is. And the other one is the instantaneous rate of change. So we actually have a lot to go through in this video, so let's get started right away with the definition. So consider a function f of x, and then for each point a in the domain of f, we consider a certain limit. And the limit is x goes to a, f of x minus f of a divided by x minus a. And if this limit exists and is a finite number, then we call this limit f prime at a, which we then call the derivative of f at a. And maybe this definition appears a little bit arbitrary to you now, but you will see that this is a fantastic object. It is a super duper invention. I think it goes back to Newton, or maybe it's even older than this. So first of all, look at f of x minus f of a divided by x minus a without the limit sign. And this also has a name, and this is called the difference quotient. Now see what happens if I give this a name. So let's call this maybe m. And then I multiply with x minus a. So what I get is f of x minus f of a is equal to m times x minus a. Now this looks awfully lot like a straight line, right? But which line? Which line does such an equation describe? Well, the answer is on the next slide. The secant line. So let's look at this graphically, and I draw an arbitrary curve. So here's the x-coordinate and here's a curve. And then I choose 2 points. I choose a point A and I choose a point x. And then the function value at a is f of a, which is here, and the function value at x is f of x, which is here. And then I draw a straight line through the points a f a and x f x, which then is the secant line. And now, what is the slope of the secant line? Well, that's easy, right? We just have to compute rise divided by run. So the rise is this bit, and the run is this bit. And so then we have f of x minus f of a divided by x minus a, which was exactly the difference quotient from earlier. So it turns out that the difference quotient is the slope of the secant line. Now, what happens as x approaches a? So then the question is, what happens to the secant line in this case? And to see that, I have a wonderful animation which you can find on WebAssign, and it has been produced by Nelson Publishing. Here you see the parabola, the function f of x equals to x squared as a black line. And then you see 2 dots. The red dot would be my value a, and the blue dot would be x and f of x. And there I have a distance of h here. Now the blue line is the secant line between AFA and x f of x. And now on this slider I can move the points around. They always keep the same distance. And the secant line, the blue line, dances around a bit. But here I can make the distance smaller and smaller. And now see what happens. If I move the blue point to the red point, then it turns out that the blue line at some point will overlap with the red line right here. And then if I continue moving the slider, then the secant line goes away from the red line. So now exactly at this point where x and a overlap, we have a tangent line. So the blue or red line, they are overlap now. The tangent line touches the curve. One has to be very careful because this is a limit process happening here. So let's look again at the formula, right? If we take the limit as x goes to a, then we get a 0 in the denominator. And we have f of x minus f of a, we get a 0 in the numerator. So we have 0 divided by 0. and all hell can break loose. But it doesn't. If we look at the secant lines, the blue line, it gets very smoothly to the red line, and then it crosses it and goes in the other direction. So it seems to be very, very smooth. We don't see any problem as we move the blue dot through the red dot. This gives us hope. So it might be possible actually to make use of this limit. This limit is nothing scary. It seems to be something very, very natural. So we learn from this that as x approaches a, the secant line becomes a tangent line to the curve. The derivative f prime at a is the slope of the tangent line to f at the point a, f on a. Can this be computed? And the answer is of course yes. And a nice way to compute it is to introduce a new variable. We set x to be x minus a, and then of course x is equal to a plus h. And then we substitute this into the definition of the derivative. So f prime of a was the limit as x goes to a, f of x minus f of a divided by x minus a. But now we substitute h as x minus a, so then this is a limit of f of a plus h minus f of a, and in the denominator we have x minus a, which is h. And then instead of writing x converges to a, we now write h converges to 0, because h is the difference between x and a. So here we have an alternative expression for the derivative if the limit exists. But this formula is cool because this is a formula we can really use to compute stuff. So let's come back to the parabola. Compute the derivative of f of x at equals x squared at the point a is equal to 2. We have to compute f prime, and I do it first general f prime at a, and later I substitute a is equal to 2. And let me write down the transformed formula which we just had in the previous slide. And now I can sub in what f is. So then this is limit as h goes to 0. This is an a plus h all squared minus a squared divided by h. And so we can multiply the square out. So then this is limit as h goes to 0, a squared plus 2ah plus h squared minus a squared divided by h. So there are two terms which cancel, which is the a squared and the minus a squared. And the other terms have some factors of h, so they simplify as well. So then this is limit as h goes to 0. So the first term 2ah divided by h, so the h goes, this is just 2a. And the next term is an h squared divided by h, so this is an h. Now here we can happily take the limit as h goes to 0, and this turns out to be 2a. So indeed, using this formula we can compute the derivative. Now let's substitute the number 2, so then f prime at 2 is 2 times 2, which is 4. Simple. Let's do a more complicated example. Compute the tangent line of the function y is 3x times x squared minus 2 divided by x at the point 2 and 18. So what do we have to do? We need a line through the point 2, 18, but we don't know the slope. Oh, but we do know the slope, because we said the slope of the tangent line is a derivative of this function at the point 2. So actually this has to be seen to be the point a, and this is the function value f of a, okay? And so then we need f prime at a, which is f prime at 2. Now, before I compute the derivative, I like to simplify this function just a little bit. So we have f of x is 3x times x squared minus 2 divided by x. And I just multiply out the 3x. So then we have 3x cubed minus 6. Right, the x's cancel. And now I use my definition for the derivative, so f prime at a equals limit as h goes to 0, f of a plus h minus f of a divided by h. And now I sub in this function. 3 of a plus h cubed minus 6 minus f at a, which is 3 of a cubed minus 6, and then all this divided by h. So I have to multiply out the a plus h to the 3 term, and I know this formula by heart. So this is 3 times a cubed plus 3a square h plus 3a h square plus h cubed. And then you have the minus 6, and then there's a minus 3a cubed minus 6. So, divided by h. And then again, as in the simpler example before, there are terms which cancel. So for example, quickly see that the 6 cancels, right? Here's a minus, and another minus is a plus 6, and there's a minus 6. And then the 3a cubed cancels with the first term here. Alright, the other terms stay. The remaining terms all have a factor of h in them, so we can simplify this a bit and write limit as h goes to 0. And don't forget the 3, so we have 3 times 3a square h and then divided by h. This is a 9a square. Then we have 3 times 3a h square divided by h, which is 9ah, okay? And then this other term is 3h square, and that's it. But now we can happily take the limit as h goes to 0, and these terms go away, and we keep 9a square. So then f prime at 2, that was the point of interest, would be 9 times 4, which is 36. Okay, so now it only remains to compute the tangent line properly. So now we have the slope, which is 36, so maybe call this m for our purpose. And we have a point 218 where the line goes through, so we can the slope point form for the tangent line. So then we have y minus 18 equals m times x minus 2, okay? And then sub in m, so then we have y minus 18 equals 36 times x minus 2. So y equals 36x minus 72 plus 18. So then we get y equals 36x minus 54. So this is the tangent line to this complicated curve. Here I show you another animation from WebAssign, where we can play around with the tangent line a little bit. The function is x times e to the minus x, which is a little bit more complicated function, but also more interesting. So what is shown here, you see in black the curve, and then blue is the tangent line at the point indicated. And with the slider I can move the point around, and then you can see how smoothly the tangent line follows the curve, and it's always tangent. It touches locally at one point. So here is a magnification zoom, and I can zoom in and the green box gets smaller and smaller. And now see what happens if I slide along the curve. If you look very, very close, they overlap very nicely. So here again you see a difference between black and red, but if you increase the magnification, they become closer and closer. Isn't that cool? They're really super close. Another very interesting concept, closely related to the derivative, is the rate of change. The rate of change is easily defined. So if you have a quantity and you change it from x1 to x2, then the net change is delta x, x2 minus x1. And then if you have a function f of x, then you can also compute the change in y, the change in the outcome. So the change delta y would be y2 minus y1, which is given by the function value f of x2 minus f of x1, where we use the delta symbol to indicate change. So then the relative change is delta y divided by delta x, which is f of x2 minus f of x1 divided by x2 minus x1. If we look at this closely and kind of imagine for now that x2 is x maybe and x1 is a, then we do have our usual difference quotient right here. And we have learned in a difference quotient we can take the limit. We can take the limit as x2 goes to x1, and what we get is a derivative. So we do the same thing as we just did before. Now we give it a different name. We call it the instantaneous rate of change, which we define as to be the limit as x2 goes to x1 of the relative change. Change in y divided by change in x. So we can write this out. This is limit as x2 goes to x1, f of x2 minus f of x1 divided by x2 minus x1. And as I said, as we defined, this is f prime at x1. It is a derivative at the original point x1. So the instantaneous rate of change is this. Let me summarize. So the derivative of f, we write at f prime at a, and this has been defined to be the limit as x converges to a, f of x minus f of a divided by x minus a, which is also the limit of a difference quotient. And we found that for computation it's actually easier to use this form, limit as h goes to 0, f of a plus h minus f of a divided by h. We found that this is closely related to the slope of the tangent line at a point a, f of a. In fact, the slope is f prime at a, the derivative. It's also related to the instantaneous change of f at a, and in fact the instantaneous rate of change is f prime at a. You see, so the derivative arises already in two important applications, and it will continue to arise all the time.